All right, so this presentation is going to deal with drill bits, cordless drills, surface feet per minute, and RPM. This presentation is not targeted for the manufacturing engineer or the machine operator, but they might learn something. I've intended this presentation to target the homeowner or the hobbyist. My initial idea for this presentation was to look at RPM ranges of various cordless drills and then to discuss that of all of the drill bits in an average set, there are only one or two bits in that set that are optimally suited for a given cordless drill. That is, when you're drilling steel. But since we will be talking about drills, we need to start by discussing drill bits first. Back in the day, we used to refer to drill bits as drills and the 120 volt corded drill as the drill motor. Today, it's simply corded drills, cordless drills, and drill bits. There are many different types of drill bits. You might have all of these types around your house. So considering what you may be drilling in and around your home, here are a few types of drill bits. The most common, the twist drill, a flat or spade bit, a brad point bit. It's kind of like a twist drill, except instead of having a conical point on it, it has a little tiny sharp point that makes it easier to start in precise locations in wood and soft materials. You've got a Forstner bit, and this actually cuts a cup or a pocket in the wood. And then you've got a masonry bit. Because the average homeowner, DIY person, home mechanic, or hobbyist will use twist drills more than any other drill, that's what we're going to focus on in this presentation. Twist drills come in 118 degree and 135 degree tool point angles. We're going to discuss 118 degree tool point angle drill bits. It's highly unlikely you're going to go to Lowe's or Home Depot and buy a set of drill bits that are going to be 135 degree tool point angles. You're probably going to have to, buy those online or more of an industrial supply place. So the most common twist drill is one with a 118 degree drill point angle. So we can see in the line art diagram 118, but here we can see, the included angle across the two lands. This is the land of a drill right here. This is where it does its cutting, where it actually does its cutting. It doesn't cut on the side, but that's a 118 degree angle. So the sharper point makes them easier to start, right? Because it's more pointed and it tends to start producing a chip quicker. So 118 degree drill bits cut more aggressively, but the steeper point makes them weaker. So for this reason, they dull quicker when they're used in hard materials such as steel. So they're best for softer materials like wood, plastic, aluminum, banana peels. This is fine when used in a cordless or hand drill because it is the hand and body strength of the user who determines how aggressive the drilling operation will be. 135 degree tool point angle drills, a significant difference between the 118 and 135 is that they're tougher and they wear longer. So if you'll be drilling with a drill press or a milling machine where you apply much more down pressure, use 135 degree drill bits if you can find them locally. So that's the last comment that I'm going to make on 135 degree tool point angle drill bits, but we've covered it. So when you go to buy a drill bit, you're going to be confronted with what to buy. Most common are high-speed steel bits. And you may have these at home right now. You got the white or silver bright finish, and you got the dull black oxide. Um, just an oxide coating is put on them in the process. Doesn't make it any stronger than the bright finish. Then you've got the coated high-speed steel, and you buy things that are gold coated, right? Gold contacts on your audio equipment, and the gold drill bits. Gold's better, right? Now, okay, the titanium nitride is the coating, and it's only microns thick. And a brand new drill, even the tip of it is coated. But let me assure you, the first time that you go to sharpen that titanium nitride coated drill bit, you have actually, exposed the plain high-speed steel land of that the drill. And because it's only microns thick, it's not adding that much. It's not like it's 10,000ths of an inch thick or anything like that. You might also have, the picture don't show it very well here, but you might have a dull blue coating on a drill bit. That's an aluminum titanium nitride coated drill bit. And then this last one down here is a cobalt. And yes, a cobalt drill bit is a tougher bit than a high-speed steel bit. It's a high-speed steel bit, but it's got cobalt added to it. And they're easily detected because they'll have kind of a light, kind of a burnt brown, or kind of a an amberish coating coloring to them, and that's caused by the process when they add the cobalt to the high-speed steel. It kind of somewhat burns that coating color on them. We're getting there. Now let's talk about surface feet per minute. A cutting tool can tolerate moving along or cutting along a workpiece at a specified travel measured in 1 minute. Molecules in all solid objects are always in motion. The higher the temperature, the faster the molecules move. Molecules cease to move when temperatures reach absolute zero, which is 459 degrees below zero. So what does this have to do with drilling holes? When the solid material, the workpiece or the cutting tool, heats up, the molecules move faster and faster. When they really heat up, the molecules can no longer be contained in their space, in that solid space. It's like the molecules are saying, open the door, I need to get out of here. So the workpiece and the cutting tool, they'll contain, like properties. And when those molecules leave their contained space, they tend to join with other like molecules. So, the like molecule, let's say, just choose zinc, for example, zinc in the cutting tool and zinc in the workpiece. When the molecules leave, they tend to be attracted and they join each other. So the object of cutting tool selection is to have a cutting tool and workpiece with the least amount of like properties. So where this discussion is not really important when you're drilling in wood, plastic, or whatever, it becomes a factor when you're drilling in harder materials. Friction, cutting, and surface feet a minute. When the drill or cutting tool moves along the workpiece, the friction causes the tool and the workpiece to heat up. This is where the molecules move faster and faster. Surface feet per minute is the measurement of how fast the tool can move along the workpiece. Now let's explain this in the diagram. Surface feet is used to determine the best speed, or the RPM, used for cutting. So this gray shape right here I'm using to represent the cutter. The cutting direction is from right to left. This blue area is depicting my workpiece, or the material that's being cut. And between these two dashed vertical lines, I'm just using that to represent a time of 1 minute. So in this diagram, we can see the cutter traveling along the workpiece at a speed over a time of 1 minute. Hence, surface feet per minute. Okay, so now let's start talking about recommended surface feet per minute based on different kinds of materials. So this following information was taken from Irwin Industrial Tools. Back in the day, most people used to associate Irwin with Irwin auger bit. They made these wood cutting auger bits, and today Irwin, they make the quick grip clamps. They also make auger bits, but they also make all kinds of twist drills and other types of drills as well. So they're a well-known maker of drill bits. This chart shows materials and recommended surface feet per minute values. So, but notice the harder the material, the lower the SFM, or the surface feet a minute. Let's take this chart and go all the way down to the bottom, and we can see that wood, we can calculate our 3.82 times, let's say 350 divided by half-inch drill bit, and we can come up with a really fast RPM for drilling wood. Our drill's not going to have that much RPM available to it, but in any case, that's how we would calculate that for wood. That's the softest material on this chart. But up at the top now we got aluminum, bronze, brass, cast iron, magnesium, plastics, and then we got steel. And the hardest steel we got here is a high carbon steel that's been heat treated to a Rockwell C hardness of 50 to 55. And we can see right here that if we have a piece of steel that hard, our surface feet a minute can only be, somewhere around 10 surface feet per minute. Okay, 7 to 15. Our steel, this is our target area right here, the things that we're going to maybe encounter around our house, our auto shop, whatever it might be. And the green, most particularly, is what we're probably going to find more often than anything else. So mild carbon steel is a steel that contains 20 to 30% carbon. And it has a constant surface feet per minute range of 80 to 110. And in my following diagram or slide where I calculate some RPMs, I'm going to use the value of 100. A medium carbon to high carbon steel has 40 to 50% carbon in it, and there, because it's got more carbon, it's tougher, and we're going to have a range of 70 to 80, or a mean of 75 surface feet per minute. Okay, and we're not talking about heat treating right here, but you got to have carbon in your steel to be able to heat treat it and make it harder. So you can take some mild carbon steel and you can bury it down in a forge furnace, and you can heat it up almost white hot, and you can soak it for an hour and then take it out and quench it in water or oil, and it just don't have enough carbon in it, and you're just not going to make it any harder. So I don't think you're going to make a chisel out of some mild carbon steel. And then, but anyhow, this is the chart I'm using, and it's what Irwin publishes on their website as recommended surface feet per minute values. And we pointed out the harder the material, the lower the surface feet a minute, and you will generally be drilling things like wood or mild carbon steel. So how do you calculate the RPM? Once you've determined the required surface feet a minute, calculating the RPM is quite simple. So you can use the following formula. And, this makes these girls back in math class in grade school real happy, because they were always good at math. But the equations like RPM equals 12 times the surface feet per minute divided by pi times the diameter. What? I don't think that way. But we can make this simpler by taking the values 12 and pi and making a constant out of it. So if we take 12 divided by pi, which is 3.1416, blah, 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 we come up with a value of 3.82, and we'll use that constant. So I can calculate RPM equals the quantity of 3.82 times my surface feet per minute and divide that by the diameter of the drill in this case. So my guess is that you would typically be drilling things like wood, most common, plastics, composites, phenolic resins, bakelite, things like that, aluminum, low carbon steel, that lower carbon content steel. And some examples of low carbon content steel you might find around your house might be, let's say, the deck on a lawnmower, angle iron, steel plates, steel tubing, round or square, high carbon steel, probably not likely. High carbon steel things are things you're probably going to find that's going to come out of machinery, engines or machinery. And, they're going to be things that are heat treated to a pretty high, unless it's a bracket or something like that, then it's not going to be a high carbon steel. But, it's going to be the things that you're not likely to be coming across drilling at home, and in which case it's going to take extra, knowledge and care and caution to be drilling high carbon steel. Stainless steel, possibly. Okay. Stainless steel, by the way, is carbon steel with nickel added to it, with a nickel alloy added to it. And it also, in addition to making it stainless, it also picks up some additional properties, and it's a little tougher and it's a little harder to break a chip and things like that. Cast iron. Cast iron's not just cast iron. There is soft cast iron, there's malleable cast iron, and there is white iron. In all my time machining over the years, the hardest material I personally machined was when I had to return some steel mill rolls, and they were made out of white iron, and because they rolled hot steel, they work hardened, and it was very tough. In fact, what I had to turn them with was a ceramic, not a ceramic coated, but a ceramic insert, and it was very tough to machine. You're not going to find anything like that at home. If you do, you're going to look at it and not do anything about it. Now, the point of the presentation. I wanted to look at various cordless drills, noting the high and low RPM range values, and I want to compare the optimum drill bit diameters from a typical 21-piece drill bit set. So whereas drilling wood makes little difference to the point I want to make here, my focus will be on drilling steel. So here we got a chart, and let's look at the left side first, reading left to right. We've got 3 columns, fractional, decimal, and RPM, and these represent 15 bits out of a 21-piece drill bit set. Smallest being a 1/16 of an inch, the largest being a 1/2 inch. It's sold. This happens to be a DeWalt set. It was a 21-piece set, but why only 15? There's duplicates, okay? So a lot of the smaller bits, especially the common ones like a 1/16 of an inch and 3/16 and an 1/8, because they're used more frequently, the user tends to break them more often, and therefore they put additional bits of the same size in the set. So out of a 21-piece set, we wind up with 15. So the first column is fraction, 1/16 of an inch. Anybody knows 1 divided by 16 is 0.0625. And the RPM is that factor, 3.82 times 100 in this case, divided by a 1/16 of an inch is 6,112 RPM. Okay? And so this column here is the calculation using 100 surface feet a minute for the RPMs required for a 1/2 inch largest to a 1/16 smallest. Now, the first 2 columns in yellow here is a DeWalt, and it's the same model, but this DeWalt drill happens to have 2 ranges. The low range is 650 RPM, and the high range is 2,000. All right, and So what I'm denoting down here at the bottom is the high range 650 is actually lower than the RPM needed for the half inch. I marked that with a green marker here. So the second range, when you pull the trigger, you develop 2,000 RPM. Now you're not going to pull the trigger on a cordless drill, and you're not going to creep up on it. And if you can make it turn very slowly, you're not going to have any torque. There's not going to be any power behind that. So there's no really measurable torque curve to that. You squeeze the trigger, develop 2,000 RPM, and away you go. So let's look at the 2,000 RPM. The calculation for a 3/16 drill is 2,037 RPM. So that's optimum for that DeWalt drill. So anything higher than that that's going to require more RPM, sure, we can drill at 2,000 RPM, but will we be able to drill a larger hole below that? So that's where I've depicted this in the pink shaded area right here. So at 2,000 RPM, that would be way too much RPM for a half-inch drill. Okay. As we move across, we got the Craftsman. It's only a single range drill, 2,000. The Metabo, wow, look at that, 5,000 RPM, single range. So it's great for a 5/64 drill bit, but it really sucks if you want to drill a half-inch hole in steel with it, And then we got the Milwaukee. It's a 550 to 2,000 low and high range. The Makita, low and high range. The Bosch, low and high range. Its high range is a little on the lower side. It's only 1,900 RPM. The Cobalt, the drill you buy at Lowe's, it's a single range drill, and it's only 2,000 RPM. And then the last one is the Rigid drill right here, and it's a 2-range, and it's got the lowest of any. Well, it's got the lowest high range, but it's got 500 for a low, and only 1,800 for a high range. Okay, so that's one chart that's just laying out these 1, 2, 3, 4, 5, 6, 7, 8 different cordless drills, and just denoting with these green bars where they fall in regards to their maximum low and maximum high range speeds. All right, here, so what I've got in this dashed boxed area right here is I've just kind of, first thing you can pick up on this is that all these manufacturers, they tend to competitively try to make a drill that has a high range speed in the neighborhood of 2,000 RPM, give or take 100 RPM or 150 RPM either way. The Metabo is the exception to the rule right here. Okay, so, but what we can see right here, looking at one size drill bit on either side of that, the 3/16 is the optimum out of that set, that 21 piece or 15 piece set of drill bits. It's optimally speaking for all them drills. You can drill a 3/16 diameter drill except for the Metabo. All right, so that was 7 of these 8 cordless drill bits here are optimum for drilling an 11/64 through a 13/64 hole, with 3/16 being the most optimal. All right, I can't stop yet without addressing one of my pet peeves: coolants, cutting fluids, and cutting oils. Most cutting tools require coolants, not cutting fluids. Cutting oils would only be used for high-speed steel tools. I'll give you an example of that. Let's say in a machine shop where they're cutting gears, they'll have hobs, and the hobs will be rotating around the workpiece, and they'll just be flooded in a solid drench of oil. And that's where a cutting oil is required. When these cutting oils are required, they're sulfur based. They're not motor oil, they're not 10W30 or 90 weight motor. They're sulfur based oils. Okay. another fallacy here. WD-40 is not a cutting fluid. I don't know if it's true. It can be argued. But I read an article once where the fellow that developed WD-40, that he was trying to develop a water displacement, or a penetrating oil to loosen up, rusted bolts and stuff like that. And that 40 was the 40th compound that he developed before he settled on it. Okay? But it's not a cutting fluid. The only use that I could see for that is that when you're drilling aluminum, the chips that come off of, the curls that come off when you're drilling aluminum, when they come back and they rub up against the aluminum part, then you can tend to get some galling on it. And, WD-40 can be quite helpful to reduce that amount of galling that can occur. But that's it's just a peeve of mine, people trying to say that WD-40 is a cutting oil. Baby oil, mineral spirits, motor oil, 3-in-1 oil, they're lubricants. They're not cutting oils. If you want your cutting tool to cut the material and make a chip, you sure don't want to lubricate it, right? I mean, you want it to cut in and not try to lubricate it and make it slick so it doesn't cut in. That would be like trying to scratch an itch without fingernails. You just can't get to the itch. Now, a couple of simple rules for machining right here. Whether you're drilling, milling, turning, facing, boring, there's some simple rules that we've always used in machining. You want to produce a blue chip. This produces a hot chip, and that hot chip takes the heat away from the part. If the chip is white or silver, it's cold, and the heat remains in the part. So you watch some of these guys, not going to mention any names, and they have little small machine tools, and they don't have the horsepower, and they can't take big deep depths of cut. So they take a whole bunch of little 40,000 depth of cuts, and they do that 10, 15 times, and they got more friction than they're chip producing, and all they're doing is heating it up, and the part is very warm after they get done machining, and they mic it or they put their veneers on it, and it's hot. And you know what? When that cools down, the part's going to be smaller than what they thought they just turned it to. But that's just because they don't have enough horsepower to make a proper cut, break a chip, and get the chip away from the part, or the heat away from the part in the chip. Here's a couple bonus rules right here. We used to always say that we spot for location. If you take a brad point wood bit twist drill and you put that little brad point down, boom, you're going to drill a hole and it's not going to walk on you. If you take a twist drill, it hold it as tight as you can, but it's going to walk a little bit until it finally bites and starts drilling. But when you do that in steel, you can't use a little brad point bit, so you use what's called a spot drill. And an S drill is not a spot drill, it's a center drill, but a spot drill is like a 90-degree sharp point bit, and we'd spot for location. Then we would drill it to open the hole to get the size, right? Then we would bore it for size, and then, if the drill happened to walk a little bit, in addition to boring it for size, then the boring bar would not walk and follow the hole, but it would cut its true location. So we spot for location, we drill it to open the hole, we bore it for size and final location, and then ream it. Okay, we ream it for finish. And in some cases, it might be the practices in many shops in that they might also be not only reaming for finish, but they ream for size, and they're taking a very small amount of material out. They might be taking 1 or 2 thousandths of an inch out when they're reaming it. Okay, so where do I stop? The 2 slides with the cordless drill comparisons are what started this whole presentation. I could go on to compare sets of drill bits, size, price, and number of duplicates. I could talk about coatings and how important are they really. I could talk about sharpening drill bits. I'll stop here and maybe address those topics in future videos. So, did you find this video helpful and interesting? I've always been a small-time YouTuber, but I sure would like to get some additional subscribers. And I'm creating a new channel, which I'm going to put these on, and it's going to start out with like nothing on it. And it sure would help if I got some subscribers. So if you wouldn't mind, click the like, subscribe, and even share the video if you would. And again, I hope you enjoyed this video, and I thank you.